All right, central limit theorem. First thing that I need you to know is to be able to state when and where you can use the central limit theorem. So there's two big things. First thing is if your population is normal. So if your population is normally distributed. So I'll go ahead and write that up here. And then the second one is if you are not normally distributed population, but your sample is going to be larger than 30. So in both of those cases, you can use the central limit theorem. And the central limit theorem states that if you take samples of women or people from your population, their sample averages will be normally distributed. And what that allows you to do is it allows you to solve problems just like the one that's being described here in A. Find the probability that a group of 25 women are selected, then their average red blood cell count will be above 5.1. So let's go ahead and draw our normal curve because those sample populations, those samples are going to have a normally distributed sample means. And because of the central limit theorem, this is the exact same mean as our entire population. And that's encouraging because we know that that value is 4.5. Now, things do change a little bit when you're talking about the standard deviation of a sample because it's going to be sigma of x bar, which is equal to sigma over the square root of n. So we've got that set up and we can actually start talking about the problem. We want to know what's the probability of that area being, the probability of that sample mean being above 5.1. So I'll go ahead and mark that 5.1 somewhere on my curve. And I'm looking for the area above that. So I'm going to be looking for the area. The good thing is we've got a function on our calculators to calculate the area underneath the curve, as long as it's the normal curve. And that function is the normal CDF. And when we use this function on the calculator, we've got to put in a few values. One, the starting value we're measuring from. We're going to start at 5.1. And then we're going to go all the way up to 1,000. And we're measuring that on a curve that has a sample mean. Because remember, here we've got the mean of the samples and the standard deviation of the samples. It's a little bit different. We know, because it's central limit theorem, that mean of samples is the same thing as the population mean, so I can actually just erase that little x bar, and I know it's the same thing. And in this case, I'm going to go ahead and erase the entire term, and I'm going to place in my sample mean, which is going to be 4.5. Now, the standard deviation is a little bit harder. You can't just erase that because it's not the exact same thing. You've got to calculate out the new standard deviation of the sample mean. So in this case, we're going to take the standard deviation from the population, which is 0.3. I'm going to divide that by the number in our sample, which is 25, or the square root of the number in our sample, which is 25. So that becomes 0.3 divided by 5, and when you type that into the calculator, you get a nice 0.6. So I'll go ahead and add that 0.6 into my calculator function, and when I type that in, I get, whoa, my calculator gave me something like this, 7.77 ... e to the negative 24. What that really saying is that 7.77 times 10 to the negative 24. If you're not familiar with scientific notation, it's not that big of a deal. Just know that this means that you're going to move that decimal place 24 times that way. So it's 0.000, lots of zeros, and then 777. So in other words, this number is very, very small. It's very, very close to 0. So ultimately, it's basically 0. Now, you might want to be thinking about yourself, does this make sense? Because what we've got here is we've got a curve, and we're trying to find the chance of getting a randomly selected group of 25 females and their average being above, their average red blood cell being above 5.1. Well, this shouldn't surprise you too much because if you think back to the normal curve of just the data, let me draw that really quickly. So here's the normal curve of just the data. And what's really important here to see is that there's that height of 5.1. So the chance of getting a group of 25 women and their average being above 5.1, that means you'd have to get a group of 25 women with more than half of the women above that 5.1. And when you think about it, here I'm drawing in two blocks of my standard deviation. So because what really happens is this 5.1 is equal to the mean 4.5 plus 2 standard deviations of the data. My standard deviation from the data is right there. So I already know that 95% of my data falls within 2 standard deviations, so there's only a 5% chance for you to be out here in this red area or this red region. So what this problem is asking is, can you get 25 women that have a mean red blood cell count above 5.1? So the chance of you getting 25 women where half of them are from that 5% is very, very small. And essentially what they're saying is it's impossible because you can't get 25 women that have an average above 5.1 because that would force half of those women or more than half of those women to be from this 5% of the population. And that's very, very small. So that cannot happen. Hopefully you're seeing how this makes sense. And whenever you get an answer at the end of your problem, like I did here, you stop and think about it as well, just like I did. Okay. Second part of 8, it's talking about you come to comparing your answers. These numbers are wrong, but I know that you know which problem it's talking about. It's talking about the problem right here that we solved. Okay, so hopefully you can see both the problems now. So I'm going to highlight in blue the problem from earlier, talking about the chance of getting one individual person above 5.1. And then the problem we were just talking about here is with the 25 people. So how is this different? The big deal here is that the problem on this page, talking about the central limit, is talking about the group of women. And you're really talking about their average red blood cell. Well, earlier we were talking about what's the chance of getting a randomly selected woman, one person. That's the big deal here. We're talking about an individual data, talking about the group mean, the mean of the population versus a group of people, and then talking about the mean of the group. That's the big difference there. Hopefully you're seeing the big difference as well. All right, let's go ahead and read through number 9 here. Men's heights are normally distributed with a mean of 69.5, standard deviation 2.4, women's 63.8 mean, and 2.6 standard deviation. I'm not going to solve through these problems. We've done multiple problems like this before and videos on multiple problems like this. I will pause the video, add the solutions up here, and hopefully you can see where I came up with those. All right, so I added those 3 solutions there. You've got them color-coded. Hopefully you can see that. Very briefly, want to talk about the last one. You've got a 100% chance. What that's saying, again, this shouldn't be too alarming for you. The chance of you getting 16 women and the average of those 16 being between 61 and 67. That's not that surprising because we're talking about the average of 16 women. If the regular population is already distributed with the normal population, that means the majority of women are going to be around these middle parts. We already know that by the empirical rule. So if you grab a lot of women from this curve, the chances are the majority of them will be from the middle part. So you look for the average of those heights, it will probably be, it might be below, it might be above, but it's probably going to be somewhere inside this region, just by the way mathematics works. Hopefully that's making sense. Good luck. You guys are going to do great.